Hello friends, welcome to GT Science tutorial. In this video, I'm going to explain about impurities in a crystal. This is going to be a very important video for bachelor's and master's degree student. In my previous video, I have already explained about different types of point defect along with their mathematical derivation. They are vacancy defect, Schottky defect, and Frenkel defect. In this video, we will understand about different types of impurities in a crystal. There are actually three types of impurities in a crystal. They are interstitial impurities, substitutional impurities, and aliovalent impurities. But in this video, we will only see number one, that is interstitial impurity, and two, that is substitutional impurity. The third one, that is aliovalent impurity, will be covered in our following videos. So let's start. First of all, we need to understand what impurities in a crystal actually are. The word itself clarifies the concept. Suppose there is a sodium ion over here, there is another sodium ion over here, there is another sodium ion over here. Now, in this bulk of sodium ion, if there is a chloride ion over here, then we call this as impurity because we needed these, but this came extra. So this is impurity. Similarly, like we use impurity terms in water and different other beverages as well. If they and not only that, in different metal, heavy metal concept as well. If there is anything unwanted that we don't need, then we call them impurities, right? So let's see point wise what impurities in a crystal actually are and few information about that. So a crystal is a highly ordered arrangement of atoms. We know that crystal is a highly ordered arrangement of atoms. We have already seen in crystals the atoms or ions are highly arranged in different shape. Okay, in different shape or different structure, they are highly arranged. So impurities, you can see impurities are those atoms or molecules that are different from the main components in the crystal. So impurities are those impurities are those atoms or molecules that are different from the components of the crystal. See, these are all hollow circle. Now this is a solid circle, right? This is a solid circle, you can see that. Okay, now this looks like an impurity. So this is the impurity atom. If we talk about similar type of atom or ion, and if there is one different or extra type of atom or ion, then that is the impurity, right? Similarly, they disrupt the perfect lattice structure of the crystal. Now you can see over here, this does not look perfect, right? Because of this one atom or ion. Okay, this has disrupted the crystal lattice structure of the crystal. Similarly, this defect may be intentional or unintentional. The purest large crystal of germanium had about 10 to the power 10 impurities in each cubic centimeter of the material. So in each cubic centimeter, that is a small size, right? In each cubic centimeter, we talk about cubic centimeter. Suppose this is 1 centimeter, 1 centimeter, 1 centimeter. This is a very small size. Now, the purest that we are talking about, the purest, okay, purest large crystal of germanium had 10 to the power 10 impurities in each cubic centimeter of the material. So we can simply see that with that is not intentional, right? That is not intentional. That is unintentional, but still there was impurity. Now, next point, impurities drastically alter the malleability, ductility, and electrical conductivity. Just like in semiconductor, when a different ion, a trivalent or pentavalent ion is doped, the electrical conductivity increases, right? The electrical conductivity increases. Let's see an example. In absence of impurities, if there is no impurities present, then here this is alpha alumina. Okay, so alpha alumina is colorless. Alpha alumina is supposed to be colorless in absence of any impurity, but it's blue. It's blue because of iron and titanium impurities. Alpha alumina appears colored, that is blue colored, due to the iron and titanium impurity. Pure semiconductors, I've written conductors over here, it is supposed to be semi. Okay, pure semiconductors do not conduct electricity. Like when you talked about silicon, germanium, they do not conduct electricity. But in presence of impurity, whenever we put trivalent or pentavalent impurity in that, they conduct electricity, right? That's why we talk about semiconductor with doping. When it is doped, when an impurity is added in a semiconductor, suppose this is a semiconductor lattice, these are the semiconductor lattice, silicon or germanium, then an impurity that is either trivalent or pentavalent ion will be doped or added over here. Okay, that is called doping, and then only the semiconductor will conduct electricity. So I hope you understood everything about impurities in crystal. Now let's see the different types of impurities in a crystal. So there are two types of impurities in a crystal. They are interstitial impurities and substitutional impurities. First of all, let's understand about this interstitial impurity, and then we will go to substitutional impurity. So first of all, interstitial impurity. So impurity terms, you can see over here, impurity atoms occupy the empty spaces or interstices between the host atom. Let me try to explain it properly. Suppose these are the ions or atoms in the crystal lattice. These are the atoms or ions in the crystal lattice. Okay, these could be any ions. Example, these are iron. Okay, this is all iron atom. Now if carbon is added to a very little extent, then those carbon atom will go and occupy the interstitial position due to the size difference. When the size of the impurity is very small, they will occupy the interstitial position like this. These are called interstitial impurities. I've already told you the example. You can see over here, carbon atom in iron create steel. So steel is not pure. That is the mixture of carbon and iron. Iron in a large extent and carbon is in very little extent, like 0.5 or 0.10%. That's all. Okay. Now they are usually smaller than the host atom. So they are usually smaller than the host atom. That means the impurities are very small as compared to the whole host atom. Hence, interstitial atoms fit into the open space between the bulk of atoms of the lattice structure. I've already told you the size or the radius of the impurity will be very less as compared to that of the host atom, so that they will just go and occupy the interstitial position. Okay. Now, interstitial impurity defect can be produced by bombarding a crystal with an elementary particle having energy above the displacement threshold for the crystal. So, this simply means that suppose we have an atom or ion. Now we bombard it. Bombard it means we just strike it with crystal with this atom. We just strike the crystal with this atom with a sufficiently high energy, that is the displacement threshold. Displacement threshold means this will come over here. When this atom comes over here, this will get this will feel strain. Okay, they will feel pressure. Give they will just give it a little space, and this will come over here and this will occupy the interstitial position. Now this defect increases the density of the crystal. Why does it increase the density of the crystal? You can see over here, initially there were many atoms. Now it has certain mass and volume. Now one atom came and it occupied the interstitial position. This is the extra atom, right? So mass is increasing, volume is not increasing. Volume is not increasing. So rho, that is density, will be equal to mass by volume. If mass is increasing, volume is not increasing, then obviously the value of density will increase, right? So density of the crystal increases in with interstitial impurities. Example, carbon atom in iron create steel. Now, there are certain characteristics of interstitial impurities. Let's see them one by one. Okay, so interstitials modify the physical and chemical properties of the material. They modify the physical and chemical properties of the material. Example, you can see steel is harder. Steel is the mixer, right? Iron is pure, although steel is harder and has much more tensile strength than iron, but it is also more brittle, right? This is all because of the impurity, that is interstitial impurities. They can change either the physical and chemical property, okay, either physical or chemical property. So normally maximum solute concentration can be 10%, okay. This is the maximum 10 maximum solute concentration, like this. Now, interstitial impurity can be used for storage of hydrogen in a metal. So, hydrogen is very small, right? And the atom of the metal are very large. Now, this hydrogen can be trapped over here. Similarly, like creation of large number of interstitials. Now, in if in a metal or in an atom, if there is a large number of interstitials present there, then this can lead to trapping of energy. This can trap energy. Okay, a large amount of energy might be trapped over there, and uh, this can lead to severe accidents in certain old type of nuclear reactors. Okay, so interstitial impurities can lead to severe accidents in old type of nuclear reactor. What is the reason for that? This can lead to a significant energy buildup in the interstitial position. Now, let's understand the second one, that is substitutional impurity. Let's see what it is. So, impurities atoms, these impurity atoms replace, okay, there, like in the previous case, that is in interstitial impurity, the impurity came and occupied the interstitial position. But in this case, the impurity will replace the atoms of the host crystal. Look at here. Suppose these are the atoms or ions in the crystal lattice or host atom. Okay, another atom came or ion came over here. Now this will just replace it. This will go outside, and this place will be occupied by this. Okay, are you getting me? I hope you understood. This ion replaced this ion from its position. Now this is called substitutional impurity. Similarly, let's see the next point. They are usually similar in size and chemical properties of the host of the atom. They are in similar size. You can see over here, I have made similar sized of ion. Now, the ion or the radius of these ions might be within 15% range. Okay, within 15% range, within 15%, their radii should lie. I've written that in next point. You can see over here, substitutional impurities have atomic radii that are within 15% of the radius of the host. So if the radius of the host is 100 nanometer, then the radius of this impurity could be like either from 85 nanometer to 115 nanometer. Okay, you understood it properly. Now, example of substitutional impurity is impurities of strontium impurity in crystalline calcium. Whenever we talk, like the atomic radii of calcium and strontium are very similar. So whenever we make crystalline calcium, then it is very likely that there will be strontium impurity present in that. Similarly, another example could be taken as zinc atoms in brass. Zinc atoms in brass. Brass is simply copper, right? The zinc has an atomic radius of 0.133 nanometer, whereas brass has atomic radius of 0.128 nanometer. If we see, this is within 15% range. So this is the host, brass is the host, and zinc is the guest or impurity. Impurity, I'm not talking about real guest, okay, impurity. So this impurity will be able to replace one of the host atom, and this will lead to a substitutional impurity. Similarly, another one is adding boron to silicon to create adding boron to silicon to create a p-type semiconductor. That is also an example of substitutional impurity. Now, finally, we see the characteristics of substitutional impurity. So, radii of impurity and host atom in within 15%. So I've already told you the radii of the host and impurities should be within 15%. It cannot be above 15% or below 15%. Okay. Another one is crystal structures of crystal and impurity. It should be same. The structure should be same. Or electronic structure. In place of crystal, write electronic. This make more sense. Electronic structures of crystal and impurity should be same. Now the third one is electronegativity of the uh, solute and impurity. I made a lot of typing error. I won't make that error in my next video. So electronegativity difference of solute and impurity should be comparable. Okay, higher electronegative difference will lead to a formation of intermetallic compound. So if the electronegativity difference is very high, then that will lead to a formation of intermetallic compound rather than a solid solution. We need a solid solution, right? Similarly, maximum concentration of solute can be 50%. This is the characteristics of substitutional impurity. I hope you understood everything about interstitial impurity and substitutional impurity. In my next video, I'll talk about solid solution, and in my following videos, I'll talk about aliovalent impurity. That is the third type of impurity. That is very important for your examination point of view as well. I hope you understood everything about this video. If you like the video, please share this video. I hope you understood everything about this video. If you like the video, please share this video as much as you can. And thank you for watching the video. And please subscribe this channel to make my face like this and smiling face. Thank you. Bye bye.